All right, so here we go. We're going to start in on a brand new unit that's called analytic trigonometry, and it's going to be kind of a blend of some other ideas. So it's almost like an algebraic approach to trigonometry. And some of the things that you can do sort of in algebra where you manipulate things and move things around to solve for things. We're going to be doing that same idea, but we're going to have a little bit of a trigonometry feel to it. And so one of the first challenges to an introduction to analytic trigonometry is that we do need to kind of lay some ground rules of some things that are true. And I don't think anything that I'm going to lay out in this video is terribly earth-shocking, but it is significant nonetheless. And we're going to figure out how we can do some just almost algebraic steps to actually find some answers that we previously found through the use of triangles. But we're just going to do that in a slightly different way. So the first thing that I want to do is I want to look at a simple right triangle right here. And so notice this could be a special right triangle. It could be a hypotenuse of 1 unit circle, or it could be something else. But you'll notice that you could play some games with it. And you could say like that the sine of theta was say b over c. You could say that the cosine of theta would be a over c. You could say that the tangent of theta is b over a. We have all these different little ideas. But there's something that I wanted to get to that's kind of important. And that is because this is a right triangle, these three angles have to add up to 180 degrees. So if these all have to add up to 180 and that guy's already 90, then that means these two have to add up to 90 degrees, meaning the two angles in the upper and the lower corner, these two guys right here, actually have to be complementary angles. So whatever these two angles are, somehow they have to add up to 90 degrees. So if we thought of this angle right here as, let's say, alpha, I could say that alpha plus theta has to be 90 degrees, but I'm going to use radians because I just like it better. I've told you that before. And so if I brought that alpha to the other side, or brought the theta to the other side, which is actually what I wanted to do, come to think of it, if I subtracted theta from both sides, like I said, we're going to be playing some algebraic games with this, I would get pi over 2 minus theta. So instead of calling this angle alpha, I'm going to call that angle pi over 2 minus theta. And you'll notice that pi over 2 minus theta is the same thing as calling it alpha, and somehow those have to add up to 90. But if we write it that way, you're going to see a few things. That if I were to take the sine of theta, which is opposite over hypotenuse, it's the same thing as taking the cosine if I was standing here, because the opposite b over c is the same as the adjacent b over c if I switched angles. Let's try that again. What about the cosine of theta? Well, the cosine would be adjacent over hypotenuse a over c. Maybe over here I'll write down b over c. So the cosine of theta is a over c. Well, there's something else that's also a over c, because if I switched sections, the sine would also be a over c if I changed perspective. Now, there's a tremendous amount of redundancy in what you're going to see here, because like the tangent of theta, tangent would be b over a. Well, there's another answer that's also b over a, but that's if I did the cotangent of the other angle. And so I think you can kind of see pretty quickly that there is a pattern in these values, that the cotangent would be the tangent of pi over 2 minus theta. And we could keep going. I'll write the other two because I just feel like I should finish. That the secant, which would be hypotenuse over adjacent, would be the same as if I did the cosecant and it was hypotenuse over adjacent. And the last one is the cosecant. So these are some fundamental building blocks of analytic trig, and all of these things grand total together, all 6 of them, you'll notice every single time the sign with the complement sign with the sign, notice that every single time it is this pi over 2 minus theta. So that's kind of cool. So memorizing them is not very hard because every single time it does this. And these things collectively are called our because these are complements of each other, these are called our co-function identities. So that's our first little identity set. Our second little identity set that I'd like to develop with you is a little bit of an idea about odd versus even. And as it turns out, when we go through all of the trig functions, every trig function is going to be one or the other. It's either going to be odd or it's going to be even. So I'm going to go ahead and I'm going to pull up Desmos here real quick just to remind you of something. So if a function is even, so notice that I have f of x sitting right here. If it was even, if I replaced x with negative x, I should get the same exact graph. You'll notice that I didn't. Or if I put the negative to the outside, it should be the same. And that clearly is not the case either. But as it turns out, if we start with a simple trig function like the cosine of x, you'll notice that that's a nice, easy little wave. I kind of wish this was a little bit more zoomed in. Let's try to make that a little bit tighter, negative 2 pi to 2 pi. And I'll make the bottom and top not quite so large. So let's make this maybe negative 2 to 2. So it's nice and big. Okay, so this is what a cosine wave looks like. And so let's see what happens if I try to replace x with negative x. Well, what you'll notice is when I replaced x with negative x, let me make the original function dotted so that we see it. You'll notice that the original function and the new function are the same. And so that's one of the things that we said is if replacing x with negative x didn't do anything, it made it an even function. You'll see exactly the same thing happen with the secant. The secant is this thing with these alternating u's, but replacing x with negative x doesn't do anything. So what you'll see really quickly is that both the cosine and the secant are even functions. I will put something on paper here in just a moment. Now, when we move on to the sine, what we found out is that in an odd function, if you put a negative on the inside, it should be the same as putting that negative on the outside of the function. And we'll find out if that, in fact, means the same thing. In other words, reflecting it across the x-axis is the same as the y-axis. So f of x, I put the negative on the inside. Is that exactly the same as, let's just watch it, is that the same as putting it on the outside? Actually, I don't like how I did that. So the sine of x, so if I put it on the inside, right there, is that the same as saying g of x equals negative sine x? I think I need to probably put it that way. So you'll notice that putting the negative on the inside versus the outside is the same thing. That makes it odd. The same thing is going to happen with a cosecant. There's our u's, right? But if I put that negative on the outside, it's the same thing. Now, we've seen some of these things before. Now, the tangent, you can probably see that the tangent is going to be the same whether the negative is on the inside or the outside. And so my first guess when I tried these problems is that, okay, well, so far, the cosine and the secant were even. The sine and the cosecant were odd, the tangent's odd. So I thought, well, obviously the cotangent would be even just to balance things out. But as it turns out, the cotangent, putting the negative on the inside and the outside, is the same. So just so happens that pretty much all of them are odd except for the cosine and the secant. So that's what I'm going to put on here. Let's share that. So my odd and even functions is that the evens are the cosine. The cosine of negative theta is the same as the cosine of theta. So putting the negative inside didn't do anything. The secant of negative theta is the secant of theta. But the odds over here, or would be that the sine of negative theta is the same as negative sine theta. That the cosecant of negative theta is the same as negative the cosecant of theta. And we could keep going. Putting the tangent of negative angle is the same as the negative of theta and the cotangent. So these are our angles that we start with. Now, this could have been useful in our previous unit because, for example, if I asked you to find the cosine of negative 2 pi over 3, you could have said, hey, Penner, it's an even function, that negative doesn't do anything. I could go like that and I could answer this question instead because it's faster. Or if I said I wanted the tangent of negative 7 pi over 6, I could have said, well, that's an odd function, so I could do a normal 7 pi over 6, but put the negative on the outside. That's just a little game that we can play that sometimes simplifies things. And in fact, on your last, one of your last quizzes, I asked you something about a negative sign of a negative angle. Well, that would mean I could bring the negative out to the front, and it would be the same as this thing because the negative here would come in front and cancel this one. So it's kind of cool little ways that you can manipulate those things using either co-function identities or odd and even identities. So what you will see in the homework is a few problems where they will ask you something like this. If the sine of theta is, let's say, 2/5, what is the cosine of pi over 2 minus theta? Well, automatically I know, according to this little rule, that the cosine of pi over 2 minus theta is directly the sine of theta. So this answer would be 2/5. We might actually change that up a little bit, and we might say something like, if the cosine of theta is 1/3, let's make it negative 1/3. Then what is the sine of pi over 2 minus theta? Well, this would be the easy question because the sine of pi over 2 minus theta, right here, the sine of pi over 2 minus theta is the cosine of theta. We could have done that. But I'm going to make this a little bit harder. What if we change that to the sine of theta minus pi over 2? Now you'll notice that this is not the order with which these things should be written. It's not right. So what I'm going to do is I'm going to show you how we play the analytic trig game. I'm going to start by factoring the negative out of this. And I'm going to change it to a pi over 2 and a minus theta. Now if you study that, this negative would make that pi over 2 negative. The double negative would make theta positive. So this is looking more like what we wanted, but we don't want that negative in the inside. So now I'm going to blend something. I know that this almost looks like the cosine function that we wanted, but we also want to remember that we said that the sine was an odd function, so I could pull that negative to the front. So I'm going to pull the negative out of that thing, and that means this is the cosine. See, all of this is the cosine, which I already said was negative 1/3, but then that negative comes into play and makes it a positive 1/3. So that's just the very opening pieces of analytic trig. So that's going to be just the very opening piece. I'm going to come back with a second video to actually go a little further into those. And in that second video, I'm going to develop another piece, and then we'll do some examples within that. But I want to keep them short, so I'll be back in a little bit with a second video. Bye-bye.